So let's take this idea of heat and let's apply it to reactions. So we have two types of reactions in terms of energy. We have endothermic reactions, and endothermic reactions are going to be reactions in which energy is absorbed by the reaction. So if we were to look at an endothermic reaction in terms of a graph, it's going to look something like this, where my potential energy is going to be on the y-axis, and my time is going to be down here on the x-axis. And now when we write a reaction, we know that reactants are on the left, products are on the right. So in terms of our graph, reactants are still on the left, products are still on the right, and the difference between the amount of energy the reactants start with and the amount of energy the the products have at the end, that is our delta H, which we call enthalpy. So enthalpy is simply going to be defined as the change in heat during a reaction. All right, so the enthalpy, or delta H, is the change in heat during a reaction. Now, a couple of other things for us to look at in terms of our graph. Up here at the top, all right, this is basically where the reaction gets started. So in an endothermic, heat must be added. At this point, the reaction starts and we create our products. So the amount of energy from where the reaction starts to where the reactants were originally with energy, we call that the activation energy, which we write as E sub A. And we've talked a little bit about activation energy, and you've heard about activation energy in previous science courses. And so we know that activation energy is the amount of energy needed to get a reaction started. Now, we've also talked about equilibrium, and we know that a lot of reactions, the reactants become products, but the products also become reactants. So the change in energy from where the products are to this activated complex right here where the reaction starts, this change is our E sub A prime, which is the reverse activation energy. So the amount of energy needed for the products to become reactants. I might have said that backwards. For products to become reactants is what I meant to say. So that is the amount of energy needed for products to go back to reactants if we were talking about an equilibrium type of a problem. So that is an endothermic reaction. And you'll notice here our delta H value in an endothermic reaction. Delta H is found by taking our products and subtracting out our reactants energy. So if our products have more energy in the end than our reactants, it will give us a positive value. So the delta H of an endothermic reaction is going to be a positive value. Consequently, on the other hand, we also have exothermic reactions. Okay? And in an exothermic reaction, energy is released by the reaction. So if we were to draw our same type of graph where we have our potential energy on the y-axis and our time on the x-axis, if we are releasing energy, then we're going to see a graph that looks something like this, where the products will have overall less energy than the reactants. So if we wanted to find our delta H, this is the change in heat during the reaction. A smaller value for products minus a larger value for reactants is going to give me an overall delta H with a negative value. And once again, positive and negative in chemistry do not give us magnitude. They tell us if something is absorbed or released. Now, if we were in a lab and we were doing an experiment, we can think about an experiment in the terms of two parts: the actual reaction itself and then the surroundings. This is everything else. All right, maybe it's the solution that the reaction is happening in. It is everything else. We cannot specifically measure the reaction. The only way for us to measure the reaction is to be able to measure the surroundings. So we can only measure the surroundings. We then have to apply it back to the reaction. So if I was to take a substance, put it in a solution of water, for example, and allow a reaction to occur and measure temperature, I'm measuring the temperature change of the water. The water is not part of the reaction itself. So I'm measuring the surroundings. You will hear that, well, let's just write this down. Let's say, okay, there is no way to measure the reaction, so we must measure the surroundings. And apply it to the system. So what is the system? The system is the reaction. All right, so when we talk about the system, we're actually talking about the actual reaction happening. All right, so let's think about this. So if delta T of the surrounding decreases, so I measure the change in temperature and I see a decrease. For example, maybe it went from 50 degrees Celsius down to 30 degrees Celsius. So the surrounding has seen a decrease in temperature. That means the surrounding has lost heat. Why did the surrounding lose heat? Because the reaction absorbed heat. So the reaction took heat away from the surrounding, making the reaction itself endothermic. So this is where students get a little tricked up, okay? Because they see a decrease in temperature and they don't realize that decrease in temperature is from the surrounding itself, all right? Not because of the actual reaction. So sometimes students will get this tricked up and make something which is endothermic exo or exo endo, but keep in mind we are always measuring the surrounding, so that we have to then apply to what was happening within the reaction. So if the reaction heat is being absorbed, then the reaction is endothermic. So in this case, Q of the system is going to equal negative Q of the surroundings. So remember from our previous lesson, we saw that Q, if Q was positive, we said that energy was being absorbed. So if Q is of the system that is endothermic, that is positive, meaning the heat of the surroundings is negative. Now, the Q of the system equals the Q of the surroundings in a closed system. So if we were able to keep all of the heat within the entire reaction and the system surroundings, the whole thing, if we were able to keep all of the heat, none from escaping out into the environment, the amount of heat absorbed by the system will equal the amount of heat lost by the surrounding. So if delta T of the surrounding increases, so maybe I went from 20 degrees Celsius to 45 degrees Celsius. All right, so I have an increase in temperature. That means the surrounding has gained heat. Where did that heat come from? It came from the reaction. The reaction released heat into the surrounding. So the reaction has released heat. The reaction itself is exothermic. So heat has been added. So the reaction released heat and is going to be exothermic. So in terms of the amount of heat, the heat gained by one is the heat lost by the other. Since the reaction itself is losing heat, that is going to be the negative Q in this case. Where is that heat going? It is going to the surroundings. So again, the amount of heat lost by the reaction will equal the amount of heat gained by the system. So let's do a practice problem, and let's look at this in terms of a chemical reaction. And now this is going to be the worksheet that I have placed onto the website for you called Thermochemistry Calorimetry. All right, so a calorimeter is just basically a piece of equipment that keeps the system closed so that there's no heat loss to the environment during the reaction. So let's look at number 2. So part A, well, it says when 12.8 grams of sample of calcium chloride dissolve in 75 grams of water, we have a temperature change from 31 to 21.6 degrees Celsius. So here's our reaction. All right, potassium chloride is going to be added to water. And so we know that ionic compounds dissociate into their ions. And now potassium chloride is in its solid form. So let's add in our states of matter. So when I dissolve something, I create ions. So I have a potassium and a chloride ion. All right, part A asks us to find the heat released by water. So the heat released by water, that is going to be Q equals M C sub P delta T. Here's my heat, the mass times the specific heat times the change in temperature. All right, my mass of water according to the problem is 75 grams. The specific heat of water in its liquid form is 4.18 joules per gram degree Celsius. And my change in temperature according to the problem is I started at 31 and I ended at 21.6 degrees Celsius. So when I plug this into my calculator, I get negative 2946.9, and we want to stick to the rule of 3 here. So that is negative 2950 joules. And again, the other way for you to write this is a positive 2950 joules, and you just simply add in the word release. So either one of these would be acceptable. B, find the enthalpy in kilojoules per mole. So you'll notice in this problem, enthalpy is in kilojoules per mole. And this brings me back here to our enthalpy, change in heat. This is going to be measured in kilojoules. So the amount of energy change we can actually measure per mole of substance. So if I have 12.8 grams of potassium chloride, I can convert that into moles, where I know 1 mole equals the mass of potassium chloride from the periodic table. So 1 potassium and 1 chlorine is 74.55 grams. So unit 2 is back. So here's my mole. Now, I've already figured out the amount of heat released. So I am going to take the heat released, which is in joules, and I am going to convert that into kilojoules. And I can go direct where 1 kilogram is 1,000 joules. So that is going to give me a value of negative 2.950 kilojoules. Now, Ms. Colson, do I have to show this conversion? If you are able to take joules and go straight to kilojoules, that is fine. You do need to show this conversion from grams to moles, okay? This you have to show every time. But our conversion from joules to kilojoules, if you're able to look at that value and just simply say, oh, negative 2.950 kilojoules, that is perfectly fine, okay? So we want kilojoules per mole. So I'm going to take this. I've already found my kilojoules, negative 2.950 kilojoules per mole of substance, which is 0.172. So when I plug that into my calculator, I get negative 17.2 kilojoules per mole. So the enthalpy, the change in heat of the reaction for 1 mole of substance is negative 17.2 kilojoules. And this makes sense that we are negative here, all right, because we are seeing a change in temperature. where it is going down. All right, so we do see a decrease overall in temperature. So heat is being released.